Yes, thank you. Yes, so as you said, there will be two lectures today. They're not completely related, but I will tell you what the difference is. In this first one, I will teach about cryptographic design. So how, yeah, you know always that when we have a hard problem, right, we can build cryptography from it. Yeah, we cryptographers, especially in public key crypto, we like these computationally hard problems. And so, yeah, when you see the schemes divided or classified into these 5 families of is it code-based, is it multivariate, is it isogeny-based, and so on, that refers to what the underlying hard problem is, what field of math it relates to. On the other hand, whether you can use the hardness of that problem, the one-wayness of the function that you have, in cryptography depends on the design, right? Whether someone has come up with a way to kind of put this into a protocol and do a key encapsulation or a signature with it. And so that will be the difference. That's why, yeah, in the first talk, I'm talking about design. So how we use, I will show you some hard problems as well. I will go to some technical details, but that is also only because of, you know, so that you have an example, so that you understand better how the protocol works. Mostly this is focused on, yeah, at a protocol level. And so when we classify them as MPC-in-the-Head, maybe you've seen in the second round of the NIST signatures, like the additional round, even in the first, not just the second, you have different distinctions than previously. You don't have these 5 families that you're used to seeing. You have, yeah, you have multivariate, isogenies, but then you have this family of MPC-in-the-Head. And that actually, it's a bit different because it refers to the design and not to the hardness of the problems. Okay, so today we're gonna see 2 such constructions. The first one is trapdoor-based signatures. So this is very relevant now for multivariate crypto. And in the next lecture in the afternoon, actually, I will show you cryptanalysis on that. So cryptanalysis on multivariate signatures and yeah, how we attack these problems and more generally, how we attack anything using this algebraic cryptanalysis approach. But that's why now I'm going to introduce these trapdoor-based signatures and I'm going to go into UOV. And then after, you know, in the second half of the lecture, I'm going to go into MPC-in-the-Head construction, which, yeah, encompasses more families. Okay, so first, as I said, trapdoor-based digital signatures. Now, currently, yeah, UOV is the most relevant example there. So, yes, for multivariate signatures, they are, if you look at the design part, they do divide into 2 kind of, yeah, we like to divide them into categories. So on the one hand, you have what we call like the Fiat-Shamir construction, or we refer to it also as the provable security construction, because there you have like a very good connection between the hard problem and the breaking of the scheme. So here examples in multivariate are this MQDSS and Sophia. We will not talk about that kind of constructions today. Today we will look at this other thing that is trapdoor constructions, and these are taught as more ad hoc signatures because you don't have this clear distinction between the hardness of the problem and the scheme. Like you will see now an example and you will see concretely why if even if I manage to break UOV, it doesn't really mean anything for the hardness of the MQ problem. Yes, yeah, the multivariate signatures are related. We see them as multivariate because they relate to the hardness of solving multivariate systems of equations, but you don't have immediately that if you break it, if you break the system, you break the hardness of the problem. We do really like those properties. This is what we have in the provable signatures, because there, yeah, you have this kind of link that says if you break the underlying hard problem, sorry, if you break the scheme, it means that the underlying hard problem, you can also solve it. And then this gives us confidence that we cannot break the scheme, because these are problems that we know since a long time ago. Okay, so that is kind of the distinction. And in the second part, the MPC-in-the-Head that I'm going to show you actually goes more into this category. It is a Fiat-Shamir construction. Now first the trapdoor one, and I will focus on UOV. Okay, so first, yeah, I still have to tell you what is the underlying math of this kind of constructions. So I mentioned this MQ problem. MQ stands for multivariate quadratic. So here, concretely, you have, let's say, a quadratic system of m equations in n variables, right? This is what it looks like. So imagine polynomials, and they are quadratic. So at most, all of the monomials are at most degree 2. We focus on the quadratic case and not higher dimensions because, yeah, this is kind of like the hardest one. In theory, I mean, of course, it gets harder in higher degrees, but not enough so that, yeah, the trade-off is good. And we don't do the linear case. Why? You know, solving linear systems of equations, that is easy, right? You do Gaussian elimination, and you can get either one solution or a description of yeah, your solution space. Okay, so concretely, it says here, yeah, you're given m multivariate quadratic polynomials, f1 to fm, and they are polynomials of n variables over some finite field fq. And then your goal, what is the hardness of this problem? The goal is to find a tuple, so like or if you want an assignment of your variables, such that all of these equations evaluate to 0. Okay. And yeah, as I said, this is hard in general. Like if you take a random MQ instance, if you just randomly create your system, probably this will be a hard instance. But there are some instances of MQ, you know, if you have a lot of structure, if not all monomials exist and so on, this can be an easy instance, okay? So there exist some MQ instances that are easy. You will see a very good example here. But yeah, imagine if you don't have all monomials, if you have only like, let's say 2 monomials occurring, then you can just linearize them and treat them as variables and solve linearly. Or there are many, many different ways that you can make a structure that's that makes the polynomial system easy to solve. And this is what we use as this is what we call a trapdoor, okay? So how do we use this, this harness? This is the trapdoor construction. So you have 3 components in the, let's say in the secret key. I will relate later to what is a key here. So you have the central map that I denoted F here. And that one will be a system that is easy to solve, okay? So you have a way, you can, easy to solve meaning you can invert, you can find pre-images of any vector. And then you also add to this 2 transformations, so 2 bijective linear mappings, so that you kind of obfuscate this so that we cannot see the structure, we cannot see what makes the system easy to solve. And these 2 linear maps, I will call them here S and T. Okay, so S is the linear transformation on the input, right? I'm making a linear combination of my input variables. And T is a linear transformation on the output. Okay, I'm transforming the equations. I'm making linear combinations of the equations. Okay, so the hope here is that even though F has some structure that makes it easy to solve, when you multiply the input, when you transform the input with S and you transform the output with T, you get another system that looks very much random. It looks like it's not easy to solve, and it is also not easy to solve if you don't know the transformation back. Okay, so that is how we build a trapdoor. Our private key is going to be this F, T, and S. We know everything. And then the P is going to be like a public key, something that everyone knows but cannot invert. Yes, so again, that is the main idea. And here with an image. Yeah, by the way, just interrupt me if you have questions, right? It's better to understand everything in sequence. And I do have time to tell you everything. So yes, this is the same workflow, but in a diagram. So how can we find a pre-image of this, let's say, of this P, if we know this other 3? So let's say, yeah, I'm given this W that is a target vector for which I want to find a pre-image of. Then first, I'm going to apply this, the second linear transformation. This was the transformation on the output, the inverse of that. Okay, so I get another X. And then for this X, I want to find a pre-image under this F. But remember, F is very easy to invert, so I can do that as a signer if I know F. And I get this Y, and then I also need to kind of, because I did this linear transformation on the input, I also need to revert it again, okay? So then when I reverted this, I get some Z, some vector, that actually, if you input it into P, so this other system that is, that corresponds like kind of to the same system up to isomorphism, this Z, if I input it into P, I will get back W. Okay, so these 2 systems, this S and T that I kind of introduced, they are an isomorphism. I think I speak about this later. Yeah, I will tell you still so that you understand. So they preserve solutions. They preserve the number of solutions, but they kind of there is a one-to-one mapping between solutions of F and solutions of P. Okay, so if you know how they relate, if you know the isomorphism between both, and if you can find solutions to the one, of course you can find solutions to the other. This is what it describes. Okay, so how do we build a signature out of this? Yeah, let's do the recap. So I have here the diagram that I have for signatures. So you know, you have Alice and Bob, and then Alice wants to sign something and convince Bob that she was the one that signed it. And as with any signatures, as with any signatures that you will see here, it's not exactly like you know for the RSA. Everything that we see in this school is mostly you want to convince the verifier that it was you that signed this message because you show that you have knowledge of something that only you can know about because you have the secret key. So in this case, what are the... And yeah, this is the flow of the signatures. Let's say this is the private key of Alice and this is the public key of Alice there. And then she signs a message. She sends the message alongside with the signature, and then when Bob receives it, he has Alice's public key because everyone has Alice's public key, and he can verify this. Okay, so concretely in these trapdoor constructions, what are the private and public keys? As I said, the private key is going to be this central map F, also the linear transformations S and T, and then that is the private key, and then the public key is going to be this P system. Okay, so let's say we have this message M here. This is how the signing works. So first, we obtain this W that we had on the diagram by taking the message, usually also a salt there, but yeah, I didn't include it here, and then you hash it. Okay, so you're not signing directly the message. Of course, you want to hash first the message so that you have like you touch everything in your universal domain, so that your target, let's say your target vector omega here is not is completely random. It can be any vector that you can expect. Then so you hash the message, and that is the thing that you have to sign, this W. And so then you go through this construction that I described before, right? It was in the diagram. So you obtain X by inverting with T first. Then you invert the central map, and then you get this Z, like in the diagram, okay? So you find a signature. You find a pre-image, actually, of this public map P. And then you send both the message and the signature, yeah? Notice here that I just send the message in clear. I'm doing signatures here. I don't care about the encryption. These are separate things, right? This takes care only of the signing part. Convincing Bob that Alice is the one that produced it. And then, when Bob receives this message, he can first hash the message, right? So he knows what the target is. So he obtains W as well. And then he gets this signature, this Z vector. He plugs it into the public map P. And this is easy because this is, you're not inverting the map. You're not finding a solution. You're evaluating the polynomials, right? And so he gets some W prime, and then he just needs to check whether this is indeed a solution to the system. And that means that Alice did a good job with the signature. It means she knows the secret. She can invert the map. And then he gets the message if the verification works out. Okay, so what is, I will still, these multivariate and trapdoor-based schemes, they are considered to be ad hoc, and we look at the security of each separately. I will point you to a relevant hard problem, but you will see that the hard problem is also a bit ad hoc because you have to, there is something that, that depends on the scheme. Okay, so it does relate a bit to this isomorphism of polynomials. Okay, I will first tell you of a related problem, and then I will tell you the one that UOV relies on. So this isomorphism of polynomials problem is the following. So if you are given two M tuples of multivariate polynomials, so meaning you are given two maps that are isomorphic, right? This F and this P, okay? Can you find these linear transformations S and T? Okay, so how does one relate, how do we go from one system to the other? And actually, we have this, right? But we almost have this. We don't have the F given. Here in input, I put both F and P. And this actually, when you have both F and P, and when you have the problem is hard if you have two transformations, S and T. Actually, the problem is very easy if you have only one transformation, S. I do stress this because it relates to U of V later, so that I kind of solve some ambiguities here. As I told you, this is one hard problem that we know of, but it's not exactly the hard problem that we are interested in for this trapdoor, right? Because here we also didn't have the F. So this actually relates to the extended isomorphism of polynomials problem. That's what we call like the problem underlying the scheme. So you still have, as input, you have only P, so you have the public map. And you also have like a description of what your central map, the structure that it has. So I say here it is a special class of polynomial systems. So you know what the central map looks like, you just don't know the concrete instantiation. And then again, your goal is to find either the isomorphism or find also, which will also give you the central map F, which is what you want. Okay, so these trapdoor-based signatures rely on this second problem. And you see this, what I talked about, why we don't know so much about the hardness, because of this special class, right? So whether this is hard or not depends on what the central map looks like, whether it is something easy or not. Okay, so that was a bit more on an abstract level. I will give you a concrete instantiation now with U of V, and this will make even a lot more sense. Okay, so as we said, U of V, it stands for the unbalanced oil and vinegar, and you will see in the second lecture why. Well, you will see even now why it is called oil and vinegar, but the unbalanced part, why we need it to be unbalanced, you need to see cryptanalysis for this. Okay, so how does U of V use this trapdoor? This is the U of V introduced by Kipnis, Pataran, and Guban in '99. The way we make a polynomial system that is easy to solve is the following. So you divide your variables in two sets, okay? So you will have 1 to V, they will be called vinegar variables, let's say. And then you have oil variables for the rest. And then all of your polynomials in the central map will look like this. So you have quadratic monomials that contain 2 vinegar variables. That is the first part there. You have also quadratic monomials that contain 1 vinegar, 1 oil variable, and that's it. You can have some linear terms, but in terms of quadratic monomials, you do not have monomials that contain 2 variables that are both oil, oil. Okay, that's why we call it like oil doesn't mix with oil. Why does this make the problem easy? Well, the way we constructed the central map is that if we enumerate all of the vinegar variables, what are you left with? You're left with a completely linear system, right? Because there were no monomials that were comprised of oil and oil. So if all of the other variables disappear, there won't be any quadratic monomials. And as we said, linear systems are easy to solve. You still need to set this up properly. So you need to have, let's say, the way that U of V does it is that you need to have as many equations as oil variables. That is convenient, right? And you have even more vinegar variables. Okay, so that means that when let's say I have oil variables and I have equations, so when I enumerate all of these, then I'm left with a linear system of as many equations as variables, and you know that one has probably a unique solution, or it is inconsistent, but if it is inconsistent, you need to do some different enumeration here and try again. Okay, so that is how you invert the central map, and that is why it is easy to do this, if you know the structure. And specifically in U of V, this this transformation on the output doesn't exist. Okay, that is in general for trapdoor signatures, but for U of V it doesn't exist because you will see better when I show you the matrix representation of this, but doing a transformation on the output doesn't do anything for the hardness of the problem, actually. And so this makes the extended isomorphism, this makes the isomorphism of polynomials problem behind U of V be like the isomorphism of polynomials with one secret, which is thought to be easy. It is really an easy problem, but U of V doesn't rely on that, actually. It relies on the extended one because we don't have F, we have only a description of F. Okay, so to understand a lot of things this afternoon and also the key generation now and all, it is convenient to look at these polynomials as matrices instead, so in their matrix or in their array representation. Okay, so this is how we can represent quadratic forms as matrices. Maybe you've probably seen this somewhere. So if you have a quadratic form, what I mean by this, it's a homogeneous polynomial. It's a degree 2. It has only degree 2 monomials. If you have a form like that on top, the f of x, then you represent it with this matrix F by putting, yes, let's say here, gamma 1, 1 is the coefficient in front of x1, 1. So you put that one in the entry 1, 1. Then in the entry 2, 1, you put the coefficient of x2, x1, but over 2. And yeah, it follows like that everywhere. So on the diagonal, you have the actual coefficients, and everything else is divided by 2. Why do we represent it like this? Because if you multiply, if you take a vector x and you take this coefficient matrix here, you multiply them, and then you multiply with x on the other side, you obtain exactly this polynomial. So this works out for a lot of everything that we want to do, key generation, signing, we can look at it as matrices. It will be more relevant this afternoon. And then there is also a way to represent bilinear forms. Actually, maybe I should have put this on the other slide so that you don't forget by then. For now, I don't need it. But yeah, if it's a bilinear form, there's a different representation. Bilinear, what I mean is like you have a different set of variables. You have variables in x and y. You can distinguish between the two sets. So in that case, and if you have a system that has only monomials that are linear in each set, but they are quadratic, and so you have x I times yj. Then the representation of bilinear maps is like this. So I just put yeah, the coefficients of, let's say, gamma 2, 1 stands in the second row and the first one. So again, we get that when we multiply x on one side with this representation times y on the other side, you get exactly back your polynomial. Okay, this will come up later more. Okay, so what does the U of a central map looks like, right, with this representation? If you put the vinegars variable first and you put the oil ones first, some people do it the other way around, so don't get confused if you see those representations. Then you see everything here that is gray, it means there is a coefficient, there is something, I mean, it is a non-zero, potentially non-zero coefficient. Everything that I put in white, it is exactly 0. Okay, so why is it like this? Because you see you have vinegar with vinegar variables, you have vinegar with oil variables, right? And these are symmetric matrices. And then oil with oil, you have 0 everywhere. Okay. This is what the maps of U of V look like, and it makes it even more clear now why we don't do the transformation on the output, right? If you do a linear combination of these, it's not going to change the main structure. It's always going to be a 0 in this block down. Okay, so that's why U of V doesn't do it. Okay, the key generation. I'm going to show the key generation in matrix representation, right? So you, let's say, well, there are two different ways that people look at U of V nowadays. You can look at it with the oil space, or you can look at it with this trapdoor construction. I'm only going to show the trapdoor one, but we're going to see the oil space and that description in the afternoon. So if I follow this, yeah, let's say traditional description, we have that for each of the polynomials in the central map P. So let's say, and these are the matrices representing those polynomials, right? I'm denoting matrices here. So you always have that the kth matrix P is equal to S transpose, this was the linear transformation, right? Times central map, the kth matrix of the central map times S again. Okay, this is how you go from, if you take something, if you take a central map F, if you want to build P from that, you take each polynomial and you transform it into a matrix and you multiply it with S on both sides, S transpose on the left and S on the other side. Why does this work? Why does this give you the P that you wanted in the other description? Well, by definition, this is what I had, right? I have F composed with S, it gives me P. If I write this a bit differently, so what does this mean in matrix representation? We need to have, from what I showed you, right? I want to have, if I multiply, yeah, this is evaluating a polynomial P, right, in matrix representation. And on the other side, I'm evaluating a polynomial F in matrix representation. But here I have a transformation on the input, right? I have S times the vector. Okay, so this is what it looks like in matrix form. And if I remove the transpose now, you will see that, yeah, this is exactly what I get. So x transpose times this times x is equal to x transpose times this times x. So it means that this is equal to that. Okay, so that's why if you want to do key generation, you pick your f, you pick your s, and then you infer p like that. Okay. And in the NIST competition, we had a lot of UOV schemes. Now, I mean, in the additional call for signatures. In the first one, it was mentioned yesterday, there was a rainbow, for instance, and that was a very structured UOV type of scheme. And then it was a very good contender for a while, but there is an attack on that that is not exactly like polynomial time attack, but it is still the attack is so good that if you need to up parameters so that rainbow is still secure, you will get something that is bigger than UOV itself. So there is no point of using rainbow anymore when you can get the same performances with UOV. Okay, but then, yeah, just simple UOV or even other structured variants of UOV are very interesting because we have very good signature sizes with this. So yeah, in the new call for signatures, there were seven variants of UOV that were submitted. So here, let's say this first one is actually just the UOV without any structure, the classical description. Then a TUOV that had some attacks. It's yeah, I don't remember exactly the structure that it had. Prov, it is turned toward the provable side. It makes it a bit, I don't know if it's less performing, but yeah, it goes towards more security. All of the others go towards maybe less security, doing riskier stuff, not less security, doing riskier stuff at the academic level, but obtaining a lot better performances to see whether this works out. So Mayo, Vox, and so on. Is an example why are these signatures so interesting? Because yeah, this is, let's say, the performances that you get for the classical UOV. So you see you have very, very short signatures. Here, this is signatures plus salt, so it's only bytes, right? It's very, very convenient for the signatures. But then on the other hand, you have huge public keys. All of these mobs that you saw, this P to the K, right? All of those are in your public map, so they are big matrices. So yeah, it is very specific in the sense that we have very big public keys, but we have very small signatures. So yeah, interesting for some applications. And yes, people are trying. Of course, yeah, it's the everlasting battle of adding structure to your systems to make them more efficient. But yeah, whether this structure brings more cryptanalysis, you have to wait and see. We choose parameters here. N is the number of all variables, right? Vinegar plus oil, and M is the number of equations, so also the number of oil variables. The parameters are usually chosen such that N is about 2 times 5 M, and you will see this afternoon with the attacks why this is chosen like that. This is for cryptanalysis purposes. So that was in the first round. Then these are the candidates that remained in the second round for now. So the others, there were, Vox had some attacks. Now we have the classical UOV, Mayo. Mayo is very promising and like a very interesting candidate, and but a very new construction. So everyone wonders about the security of Mayo still. But yeah, it's been already 2 years since the submission, so now we have a bit more understanding. Snova is also a very structured system, and actually it turns out that it looks a lot like Mayo. It has something, if you change the description, and that is how Bulens found his attack now, because it found the relations between Mayo and this, and then they didn't do some countermeasures against attacks that Mayo did. And then QRUOV is over quotient ring, so also very structured. Yeah, we'll see. Okay, so these are the candidates that remain in the second round, and we'll talk about how we attack these systems in this afternoon. Yes. Yeah. So Snova went to the second round, and actually in the second round so the attack was before the submission to the second round. So they did do, I haven't looked at the specification actually to see. What I know that is they did some countermeasures against this, because the attack that VART has is, it lowers the security in general also, but for some for a fraction of the keys, some weak keys, it is very, very bad. So even, that's the part that ends on a weekend. There is workarounds around this. Mayo does everything so that, you have a full rank of the polynomials. I don't know if Snova did exactly what Mayo is doing, but they did something for the attack in the second submission. I don't know if it covers everything. Yes, so that is everything for this part, for the trapdoor part. So if you have any other questions about this? No? Okay. So the second part, as I said, I'm going to tell you about MPC-in-the-Head schemes, and this relates to multi-party computation. It would have been better to call this title MPC-in-the-Head instead. So what is the MPC-in-the-Head construction? Okay, as I said, we want to do something with, it's going to be like a proof of knowledge. So the MPC-in-the-Head construction, it's very, very popular now. As you will see, like in the NIST competition, there are a lot of submissions around that. I think it was 8 or 7. We will count at the end. It is a very interesting construction. You will see why for several reasons. It has a lot of trade-offs. It has a lot of reparameterizations that you can do. But the way that I'm going to describe it to you is in these four, let's say, four stages. Okay, so first, at a very high level, you start with, you pick a problem, right? I said before, hard problem equals cryptography, usually, if you know how to do it. You pick a hard problem, this one-way function, right? And from this, you do an MPC protocol. MPC stands for multi-party computation. So you kind of, you compute something in a shared manner between several participants. We will see what this looks like. So you build an MPC protocol whose goal is to compute this value y in a shared manner between several participants. And then once you have this MPC protocol, and this, we had a lot of works on this because people that work on MPC protocols, they are a lot farther than where we are in signatures in the MPC. Like there is a lot that you can do with MPC, so it was very convenient. And then from that, you build this MPC-in-the-Head identification scheme. So that is going to be the construction. I will show you how you can go from an MPC protocol to an identification scheme. Identification scheme, it means you can prove to a prover that you are the one that you claim you are, right? That you hold the secret. But in this name, there is the notion of this is an interactive scheme, right? You have a prover and a verifier. Okay, I will tell you how this works. And then from this identification scheme, you want to have a signature instead, so you want to make it non-interactive. Okay, so the first one, the one-way function. This is actually, we choose a one-way function so that we build what we call this zero-knowledge proof of knowledge. Okay, what does this mean? I want to prove that I know something without revealing, to prove that I know a secret without revealing anything else about the secret except that I know it. Okay, so a very nice way that I've seen of, my favorite way of people describing this is like, imagine you have two pens in your hand. I don't know, these are clearly different, but let's say you can't tell the difference. If I want to prove to you that I know which is which, I know some secret, I know why they are different, then what I can do, for instance, is I can give you the pens, then you mix them up behind your back, right, and you give them back, and then I need to guess which was which without telling you how I know this. And then, if I do it once, you'll be like, okay, maybe it was lucky. It was a 50-50 chance. But if we do it a lot of times, then these probabilities multiply. And then I really am convincing you that I know something about these pens that you don't know without telling you what it is. Okay, so now we're going to do this principle, but with some mathematical properties instead. Okay, so that is it. You want to prove that you know X you know a pre-image under this Y, and you know a pre-image of Y under this F, but without revealing anything about the pre-image. Okay, so the one-way functions that are used in MPC-in-the-Head now, it goes in the several categories, and throughout the years it changed a bit. So it started off with standard symmetric primitives, right? You can build an MPC protocol, you can compute symmetric primitives in a shared manner, but it is very costly, right? Because, MPC people know how to compute both addition and multiplication in a shared way, but multiplication is pretty costly. So when you have a huge multiplicative depth, that's not very convenient. So then that's why these MPC-friendly symmetric primitives started coming up, which are different symmetric primitives, let's say, where you really want to have like a lower multiplication depth. You want to make it more efficient for an MPC protocol. But then, a bit, there are new primitives. There's more structure. We're not that confident in, and so on. And then you also have you can do this by choosing hard problems, like we do in public key crypto, right? You can choose MQ, for instance, the problem that I told you about. I'm going to tell you about another problem here. So everything that you see in what we learn in post-quantum crypto could potentially be used as a one-way function underlying your MPC protocol. Okay. And this is exactly like I said, like with the MPC framework, we can compute everything, but today I'm going to tell you why, some things are difficult. And so if you have, for me actually, if you have something that is that is additively homomorphic by nature, it is very easy to do an additive sharing on that. And that's why I'm going to describe today the things that I'm going to describe. I'm going to do it with the discrete log. Okay, so today we're going to focus on the third one, on the third, let's say, classification. And the examples I'm going to give you are of how we share things, are the discrete log and also the syndrome decoding. Why I did the discrete log, this is not post-quantum, right? We don't use it here, but it is very convenient for, from a pedagogical point of view for describing MPC-in-the-Head, because it is, naturally additively homomorphic. Otherwise, if your problem is not, if you have some nonlinearity in your problem, which you do want, of course, then you need to find some workarounds or reformulate the problem, and this is per primitive. So every scheme, every MPC-in-the-Head scheme that you see does different techniques to kind of, circumvent this. So I'm not going to go into those. We will look at them as a black box. You'll see what I'm talking about. Okay, so then the MPC protocol, yes, how do we share this computation? What is multi-party computation? I'm going to do it, I've never worked actually on protocols and on MPC, so I will do it on a level that we need only for the signatures, right? MPC is a very vast topic for people that work on it for other reasons than signatures. But I'm going to tell you what we need here only. So this, you have, as I said, this one-way function. So you have this f of x equals y. And then you can build a sharing of your secret, right? X was your secret. What is a sharing? It is you have these different shares, x1 to xn, let's say, if you divide it in n parts, such that when you sum them up, it gives you the secret. Okay, so whether this is integers, and then you have like a summation of them that gives you the x, or whether this is vectors, and then you also sum up the vectors and you get your vector, anything that is additively shared. And the goal of this MPC protocol is to jointly compute this function g. Okay, what does this function do? It accepts if f of x is indeed y, or it says reject if it is not. Okay, but the challenge here is to compute this jointly between the parties. The way that we do this in MPC-in-the-Head, we borrow this broadcast model. Okay, what does this model look like? So you have the different parties. Here you have 5 parties, for instance, and then they all have a share of their secret. And then, of course, they don't want to send each other their shares, right? Because those are secret to them. But they instead share some other auxiliary values, okay? So they can share this alphas. And then they broadcast it. So they share it to everyone. And then everyone that gets all of the alphas, all of the values, they can jointly compute whether, having all of the alphas, you can infer whether it is an accept or a reject, whether the thing that you started with, the input that you produced the shares of alpha with, whether that is a pre-image of f or not. Okay, that is at a high level. Now, how do we do this concretely? First I'm going to show you with the discrete log, as I said, and just a reminder, this is the discrete log problem, right? You have elements in a finite cyclic group. G here, probably it's usually a generator of the entire group. And you know that, well, you need to find an x, you need to find the exponent, so find an x such that g to the x is equal to h, okay? How do you brute force this problem, right? I always ask this because if you know how to brute force a problem, you know how to you know what the problem is, right? So here you would just need to choose x from, let's say, from 0 to the cardinality of your group. Try, put g to that exponent, then go another times g, and check every time whether it is an h. Okay, that is brute forcing the discrete log. Of course, there are a lot better algorithms for this. Okay, why is the discrete log interesting here to explain? Because it is very easy to share. So if you have this sharing of x here, x1 to xn, then what is happening is that g to the first share times g to the second share times times g to the nth share gives you exactly, this is equal to g to the x, right? Because you remember in the, logarithmically, the exponents sum up when the terms multiply. Okay, so it means that to jointly check whether g to the x is equal to h, you just need to have each party compute this hi, right? So this is a share obtained by, this is a value, let's say, obtained by putting g to a share of x. Yeah, you get the corresponding h. And this corresponds to the alphas that we saw in the previous image, right? There were some alpha values that, so here in this context, the hi will be the alphas, right? And then after the broadcast, what do you do to check? Well, everyone that has all the inputs of the broadcast, they can just multiply everything together and see whether this multiplies to h or not, right? Because it should multiply to h. Okay, so you see the discrete log is very nice in that sense, but yeah, the discrete log is very nice in a lot of ways that we cannot exploit now in post-quantum. So yeah, these slides with the two examples are not about post-quantum. They are about explaining MPC in the head. Okay, but now a relevant example. You have another problem that is actually quantumly hard, so and can be used for MPC in the head, but it is a bit trickier than the discrete log. So the syndrome decoding problem, I'm not going to explain too much what it is. You haven't seen a code-based crypto lecture yet, okay? So I'm not going to go into how it relates to coding theory or why we call it a syndrome. I'm going to describe it in terms of linear algebra only. And this is enough so that you see here. But tomorrow, I think you will, Simona, you will explain the syndrome decoding problem a bit in more detail. You will see why it is called a syndrome and so on. So here I tried to write it as just in terms of matrices, right? So yeah, the problem is if you're given some vector s and in fq to the k, imagine this k is smaller than the n, and tomorrow the notation is going to change a bit. And so you are given this vector s and you're given a matrix H in k times n matrix over a finite field, let's say over F2 most conveniently, but yeah, there are variants. And then you are given some integer t. So the goal of this problem, what does it ask you? It asks you to find an e, some vector called e, of length n, such that if you multiply h times e, you will get this syndrome s, this vector s that we call a syndrome, but also the weight of this e is equal to t. What I mean by weight of a vector, I mean the Hamming weight. Right? Have you, maybe you've seen the Hamming weight somewhere? It is the number of non-zero positions that you have in your vector. Okay, so those are the two requirements for my solution. I wanted to satisfy this linear constraint and I wanted to satisfy the weight constraint as well. Okay, that's the problem that we have. Visually, this is the problem that we have, right? So here I have this matrix H, and let's say gray, it means, it's any entry. Then I multiply it with this E. I want to get this S. Concretely, what does this, how do we brute force this problem? What does it look like? I put here an example so that you can see. So for instance, if this is, let's say, my vector that I want to, this is, let's say, a solution to this problem. And this is a vector where it has a 1 here, it has a 1 here, 1, 1, 1. So with t is equal to 5, right? It has only 5 non-zero entries. Well, what does the syndrome correspond to? If you multiply this, right, the first row with this vector, you will get the first one, right? The second row with this vector, you get the second one, and so on. So basically, this S is actually a sum. Well, I'm saying this over F2 now. Over F2, it will be the XOR, but yeah, in general, it's a sum. So it is a sum of the columns where E was non-zero, right? All of the columns, all of these other columns don't matter, right? Because they will get multiplied by 0 anyways, okay? So how do you brute force this problem? A bit better than going through all E. No one wants to answer this? Okay, so you wanna choose, you need to basically choose which are the 5 columns, right? We know T. Which are the T columns that you're gonna sum up? Okay, so it's N choose T, right? You choose which columns, and then you sum them up, and you check whether it is equal to the syndrome. And then if it is not, you pick another subset of T columns, you sum them up, you check whether it is equal to the syndrome, okay? So that is what the problem looks like. Why is it, as I said, S is equal to the sum of the columns where EI is non-zero. Why is this a hard problem? It looks like a linear problem, right? It looks like linear algebra. It's not a linear problem because, otherwise it would be easy, and that is because of this weight constraint, right? So finding an E such that, this is satisfied as the syndrome is equal to H times E, that is easy, right? It's a linear algebra, or you can model it with equations if you want, and you will get a linear system. Finding E of this Hamming weight is also easy, right? There are a lot of them. Well, not a huge fraction, a lot, but still a small fraction of all. But then finding E that satisfies both constraints at the same time, that is the hardness that is what brings the hardness of the problem. Okay, and that is also what is going to, actually the second constraint, the weight constraint, is what is going to make it not hard. I don't want to say hard because I don't mean computationally hard, but it's going to make it more complicated to build the MPC protocol with this. Okay, so how do we jointly check whether whether E is indeed a solution to this problem with this input S and H? Okay, so not a solution, but whether it satisfies this linear constraint. This is again easy, right? Because this is a linear constraint. So let's say each party has a share of this secret, right? The secret is now E, so each party has the party I has a EI, right? And then that means that if each party multiplies their share with H, then they're going to get a share of the syndrome. How do we recover the whole S at the end? Well, after the broadcast, what do we need to do? This time we don't multiply, we sum up. We sum up all of the shares of S, and then this should sum up to S. If you want to see it visually, right? Imagine, well, I didn't draw everything, but imagine that you share this vector in a very simple way to visualize, that you have, let's say the first vector is going to be just 1 here and everything else 0. The second share is going to be a 1 here and everything else 0. The third share is going to be a 1. Yeah, so then you get S1 is going to be what? It's going to be just this column. S2, the share, the alpha that you're sending of, the 2 is going to be just this column here and so on. So then when you sum them up, you do indeed get the syndrome. Okay, so that was the easy part. It is exactly like the discrete log. What is hard to do is check whether E, without knowing E, check whether E is indeed of Hamming weight equal to T. And this is a bit more complicated. We're going to leave it as a black box. Not only because, it is more complicated, also I didn't choose to focus on that because this is different per scheme. Okay, so this is behind the SD-in-the-Head scheme. Another scheme uses another problem, MQ. There you need to find another solution. There are some common solutions. There are some common ways to check multiplication, but for the most part, they needed to either rewrite the problem in some other way or find some workarounds to check for this weight constraint. But it exists now. Okay, so those are some examples of how you build this MPC protocol with some one-way functions, right? So now I'm going to tell you how you go from an MPC protocol to this MPC-in-the-Head ID scheme. 10:30. Okay, so this, stands for MPC-in-the-Head. I will tell you why it is called, finally like this. Okay, what is the main idea behind the MPC-in-the-Head? So we said, okay, let's say we have this MPC protocol. Let's use all of this work that we have around it. we need very little from MPC for the signatures, right? So the properties that we need to have is a bit different than, we only need a protocol that is n-1 private, okay? So that means the views of, if you have n-1 of the shares, if you have all shares except for the last one, you know nothing about the secret. And this comes from the additive property, right? It is completely random. If I want to produce a share of my secret X, I can just randomly generate n-1 things and then add, infer what is the last share, and there you have it. So that means that if you have all of the shares except for one, you don't know anything about X. X could be anything depending on the last value. And another property that we need from, it's the semi-honest property. So that means, that all of the parties are just honest in their execution. They will not try to do something malicious to the protocol. And this is a weak notion in MPC. Usually you want some harder notions, but this is enough for MPC-in-the-Head because this is, the signer is the one that does everything, basically. So we don't need any stronger properties than this. The first instantiation of this MPC-in-the-Head was the picnic family and they used the symmetric primitives, as I said. It started with symmetric primitives, then MPC-friendly symmetric primitives and hard problems. Okay, so an identification scheme, it always goes in this, we call this 3-pass or like a sigma protocol. Now it's going to be more pass, but yeah. Let's say you have a prover and you have a verifier, and the prover needs to convince the verifier that they know a secret. We do this in 3 phases. So first the prover will send a commitment, so they will commit to some value, let's say. And then the verifier will send some challenge. They will ask you a question, right? They cannot ask you what is the secret, but they can ask you other stuff around it. And then you respond to that challenge, and you should be able to respond to any challenge that the prover has, so that you prove, if you know the secret, you can respond to anything. Okay. Here, concretely, that was a bit at a higher level. Concretely, with the discrete lock, what would this look like? So remember, this is the problem that we had. We have g to the x is equal to h, and x is the secret that the prover knows. Okay, so what will the prover do to convince the verifier? First, he will simulate this MPC protocol, but in his head, meaning he will not. It's not several parties that compute it, it's the prover that computes everything, but he does he plays the role of all of the parties. Okay, so it means that the prover computes all of these values, the hi. And then the prover commits to these values h, right? It means he sends them to the verifier. He says, okay, these are my h values, keep them. And remember this because this doesn't say anything about x because the discrete log is hard. I mean, okay, so not quantumly, of course, if you have a quantum computer, this doesn't work. But if your underlying problem is hard, then you're just sending the h, doesn't give you a solution for the problem. And then the verifier chooses a challenge. A challenge will be from 1 to n. It chooses one of the parties of the MPC protocol and sends this to the prover. What does a challenge mean? It means that the prover needs to send to the verifier all of the shares except for one, and that is the one that was chosen by the verifier. So the prover sends all of the x's except for xc, where c was the challenge. Okay, and remember this was n-1 private, so the verifier cannot know anything about the secret. What can the verifier do now? Well, the verifier can first check whether all of these shares that he got correspond to the commitment that happened before. So first we check whether if we put g to the xi, it will give us an hi for all i's. And then we can do, for all I except for the one that we do not have, of course, right? So that one you cannot check. And then you also check, to know that this is like a nice sharing, you also check that the product of this corresponds to h, which was something in the, like your public key, right? That is what you wanted to convince the verifier of, that you know a pre-image of this problem, okay? So the verifier checks both constraints. If both constraints are okay, then it means that the prover did the protocol correctly. Honestly, and then he knows the secret. I will go into ways that a prover can cheat here, right? Because we asked for all challenges except for one. And this, it's relevant for the protocol, but we will go into that in a second. And you can think about it, how we might cheat in this way. How can we convince a verifier? What I mean by cheating, convince a verifier that you know the secret when you don't know it. Okay, so that was the discrete log, very simple, but actually when we go into syndrome decoding or any of the problems that you see now at NIST, it's not so easy to build this protocol, and you need some more, you need a more complicated protocol. As I said, it's not going to be a 3-pass. We use what we call the broadcast model with Oracle. So basically, like, you need some more randomness so that you can check the weight constraint. You need randomness from the verifier. And I'm not going to open this black box. I'm not going to go into detail into how this works, but that is what the model is called. And then it gives rise to a 5-pass protocol instead, right? Usually when you see MPC-in-the-Head, it's not going to be a 3-pass protocol. There are sigma protocols, there are 3-pass protocols in other schemes, not in MPC-in-the-Head. So you need something else. It's a 5-pass, or now with volley-in-the-head, if you see this keyword somewhere, that is a 7-pass even, because it's a different construction. Okay, so the protocol actually looks like more like this. So you commit to something, then the verifier sends some more randomness. You commit to something else that depends on this randomness, and then challenge and then response. Okay, but those are things, as I said, that we're not gonna go into. Okay, so what are the security properties now of this? Formally, what you want to achieve in any zero-knowledge, proof-of-knowledge identification scheme, you have 3 properties: completeness, special soundness, and then zero-knowledge. Okay, so you want completeness. What is completeness or correctness? Sometimes it just means that if the statement is true, so if it is an honest verifier and he does know the secret, then the protocol will work. He will always be able to convince the verifier. And this is usually, yeah, you look at the scheme, you see whether it works, right? You need to build the proofs that the math is mathing. But yeah, that is basically it. Then the soundness. Okay. What does this mean? That we want to have the property that a dishonest prover cannot convince a verifier that he knows the secret. Okay, so if you don't know the secret, you cannot convince the verifier that you know the secret, except with a small probability, right? We need this for the, and what I mean by small probability, this relates to your security level, right? Like if you are working on a scheme for the first NIST security level, then you want the probability of a malicious verifier to convince the prover to be 1/2 to the 128. Right? So that is how small the probability should be. And I will tell you how we get to such a probability. Another way that we describe this soundness is with the special soundness property, which is very convenient for proving. It is a bit, harder to get at first, but for proving it is more convenient. So let's say, yeah, here I'm going to describe just 2 special soundness, or in this case it should have been an N. So you want to have the property that if you obtain 2 valid transcripts of transcripts, I mean, yeah, you can see this protocol happening with the same commitment but a different challenge. Okay, so if you have 2 responses if the prover does the same protocol with the same commitments twice and answers to a different challenge the 2 times, then we can definitely extract a solution to the underlying problem. Okay, here, for instance, yeah, you know that if you do this with a different, twice with a different challenge, then you just get all the shares, right? This is straightforward. You will get everything except for I the first time, then the second time you will get anything except from J, and then you have everything, okay? So that is easy. But why do we want to have this property? That if you get these 2, of course you don't do this in protocol, if you get these 2, you know the secret, this connects to our confidence in the hardness of the problem, right? So I'm telling you that if I'm able to break this scheme, meaning break it means I can, yeah, I was able to respond to at least two challenges. I mean, if you can break it 1, you can break it twice. If you are able to break the scheme, then you can definitely find a solution to, you can find the secret. That means you have an algorithm to solve this underlying hard problem. Like if this were true, I mean, if it was easy to break a scheme that is, let's say, based on this syndrome decoding problem, how can I solve the syndrome decoding? I can just plug it into a scheme, solve it twice, and then I get my solution. Okay, so that would mean that syndrome decoding is easy. Okay, since we have confidence that syndrome decoding is not easy, then it should mean that this scheme also cannot be broken. That is what we are dealing with when we say it is not an ad hoc scheme, it is more like a provably secure scheme. Okay, so that's what this special soundness represents. And then zero knowledge is the property that if you can observe the transcript, anyone that can observe the transcript learns nothing about the secret other than the fact that the statement is true. So it completely looks like you can simulate it if you want. You can simulate a transcript of the scheme if you don't know anything about the secret even. And it will look to anyone but the verifier, it will look correctly. Okay. So does this MPC have this property? So for completeness, I'm not going to go into details. This is depends on the primitive, right? You need to see whether, as I said, the math is done correctly and whether there is nothing there that can make an honest prover respond with something that the verifier will reject. Okay, so that everything checks out. This soundness property, that is more interesting. So here, actually, in MPC-in-the-Head, you have two, this connects to how can you cheat the protocol, right? In MPC-in-the-Head, you have two ways of cheating. You can either cheat these inputs, these random inputs from the oracle that I talked about, that I didn't talk about, actually, that I just told you about. So you can try to guess this as well. I'm not going to focus on that because we don't know it. But we can also try to guess the second challenge. That is one way that you can cheat. And this happens with probability 1 over n, right? Because the challenge space is from 1 to n. Why am I saying that if I can guess the second challenge, I can just iterate the protocol even if I don't know the secret? Okay, so let's look at the diagram again. Okay, I don't know if you've thought about it a little bit. What can you do if you know in advance? If you know in advance which challenge the prover is going to choose, you can prepare for that challenge, right? So how do you do it in the case of discrete log? That is the one that is easy to describe. So if I know in advance which challenge the verifier will ask for, and even if I don't know the secret, this is what I would do with the discrete log. Okay, this is not in a paper, but it's an exercise. So I would choose this. I don't know x, right? But I can still choose some random shares. I can choose some n-1 random shares. And then, of course, I cannot complete this with the nth share because I don't know x, okay? But I have xi for I from 1 to n-1. Okay, and then I compute the shares that I would have computed otherwise. So I compute hi for everything g to the power xi for all i's in 1 to n, so everything that I have, right? And I compute this hi's. And then I compute the last hn in such a way that that this second constraint, that it checks out with the secret, right? I want it to be, here it should have been a product. Yeah, I will change it after because it's a discrete log, it's not the syndrome decoding. Yeah, this one is the product. I compute the last h this way, the h minus the product of all of the others. Okay, so then I have all of the h's, all of this alpha that we are broadcasting. Okay, so I can do a commitment that looks like a regular commitment. Okay. Sorry? Yeah, when I change it to a product, it's also going to be a division. Yes, exactly. So that was the error. This is for syndrome decoding with the sum. Here it's going to be a product. So keep in mind here that why can't we compute now the last share? Well, this is connected directly to the hardness of the problem. We cannot compute xn such that this hn that we computed works out because the discrete log is hard. Right? So this every time this is going to be the case. The discrete log is not post-quantumly hard, but yeah, here it's an example. Okay, so now you can commit to all of these h's, right? You send it as you would in a regular protocol. And then the verifier has no idea whether you're doing this correctly or not, so he will just send you a challenge. Okay, he would send you a challenge. If he sends you a challenge that is different than n, what happens? You can respond with every x except for n, except for xn, right? So you send all of the shares except for the nth one. And what will happen here? Will you succeed? The verifier will say yes or no. You remember what we were checking? So we were checking first the constraint whether g to the share x I corresponds to hi. And here it will be the case because you computed them all so that it does, except for the nth one, right? So the verifier will say yes on that. And then the verifier will also say yes on the second constraint that he checks, because also this product, yeah, here it is indeed written as a product. It works out because when you, this is how you constructed the last H, so yeah, this thing works out when I fix the slides. And the verifier says yes. Okay, so that, so you managed to cheat the protocol, right? Why did you manage to cheat the protocol? Because you were very, very lucky that the verifier sent this N as a challenge. If the verifier sends anything else but N, then what happens? This will still check out because that is how you constructed it, but this other thing will not check out. It won't be verified, and then the verifier will say no. Okay, so that's why we say that you can cheat with a probability 1 over n. Okay, and then what we do, because as I said, the probability with which you want to cheat is more on the level of security, right? So it should be 1 over 2 to the 128 for the first level. And if I have n, I'm not going to do 2 to the 128 shares, of course, because this is impossible. Instead, we have n for some smaller n, right? You can do even of 2. It starts with a 2, right? Let's say you choose n to be a 2. What you need to do in this case is that when you, as I said with the pens, when you convince the verifier once, you convince them that you didn't get lucky once, right? So with a 50-50 chance, you couldn't cheat. If you repeat this protocol enough times, then the probabilities of cheating multiply. So here you need to repeat the protocol enough times so that 1 over n to the power of the number of times is equal to 1 over 2 to the 128. Okay, so you repeat the protocol until you are convinced that you have a very negligible probability of cheating. Okay, so that is about the soundness. Is soundness clear? Huh? Okay, so then and the zero knowledge property, yeah, we said that we want anyone that looks at this transcript, they cannot infer anything. That comes directly as a result of the n-1 private property of the MPC scheme. So that is why it was also very convenient to build zero-knowledge schemes for this. We already have everything we need from MPC. Just by the fact that when you see, yes, maybe I didn't say enough here, but yeah, when you see this, what do you see in the protocol? You see the commitments, okay, and if your problem is hard, you don't know anything, you see a challenge, okay, that's a verifier. You see all shares except for one. If you're working in a n-1 private setting, then it means that you cannot know anything about the secret because you saw n-1 shares. So it is also, that's why it is zero knowledge. Okay, the last thing. So I described how you can convince a verifier, but what I was describing was interactive, right? You're saying something and the verifier is asking and so on. Ideally, what we want is a signature instead. And you did see this yesterday with the dilithium explained. So how do we go from an identification scheme to a digital signature protocol? We use the Fiat-Shamir transform. Very simply put, yeah, the goal is to, as I said, to transform an interactive scheme into a digital signature. And what we do is instead of the prover choosing the challenge, right, that was what we needed was just the prover giving us something. Instead of that, we are going to hash the message and the commitments, and we're going to get a challenge from the hashes. Okay, concretely, if I show you the diagram of signatures from before, and here I replaced it with the discrete log that we had here, and this is what changes when you go to a digital signature. So you have the commitment like in the identification scheme, but then instead of a verifier sending you a challenge, you have the challenge is equal to a hash of M and the commitments. What do I mean the challenge is equal to this? Well, imagine, I don't know, you need a challenge that is either 0 or 1, that is if N is equal to 2. Then when you hash this, you take the first bit as the first challenge, you take the second bit as the second challenge, and so on. Or if n is larger, yeah, segment it differently. That is how you get a challenge from the hash. And of course, and hashes, if you have a good hash function here, then you cannot control in any way what the challenge will be, right? Starting from the message and the commitment. And so, yeah, of course, I mean, you cannot just pick your challenges before choosing the commitments. That is the point here. The commitment is here. You cannot pick your challenges before committing. Okay, and then similarly on the verifier side, because anyone that wants to verify your signature, right? It's not an interactive thing. It's not online, but anyone that wants to later verify your signature, they recompute the same challenges from hashing the message and the commitment, and then they do the identification protocol like this. They do the verification of it. Okay, and that's how we get digital signature from this identification protocol. And of course, again, here I put the discrete log, so careful to example. And also I show the 3-pass sigma protocol. It will be a 5-pass or a 7-pass in the actual schemes that you look at. Okay, now about some optimizations. What I mean by optimizations is, what can you do? How can you modify this protocol so that you get smaller signatures, smaller public keys, better performance, and so on and so on. So there are several very interesting optimizations in the literature. There's a lot of work on this. Like if you want to look at what's happening, it is a very vast field. I'm going to go into 3 of them. Here I listed some more. So first, you can, one thing that you can do is hash the commitments. Then another thing that you can use is a seed tree. And then a more recent, let's say, optimization, more recently introduced result is the hypercube, and that is a very fun one that I'm going to show you today. And there are also threshold schemes now. So threshold I'm not gonna talk about, but these last 2, if you look at the schemes, it's either or. Okay, so you will need to choose either to use the hypercube optimization or the threshold. And different schemes chose different things in the first round. I haven't looked at what is chosen now, okay? But I'm going to go through the first 3 as a general ideas of how they are done. I'm not going to show you the entire protocols, but knowing the general ideas, you can look at the protocols and then understand everything. Okay, so hashing the commitments. What can I do better than the protocol that I described before? And if you think about the size of the signature, for instance, that one depends on what here? It depends on the size of your commitments and the number of commitments, right? That is what you send as a signature. Okay, and then the size of the public keys that is more connected to your underlying problem. Okay, but here we want to have smaller signatures. So what are we going to do? We are going to compute on the left here. The prover computes in the same way first. He shares the X, and then he computes all of this alpha, or in this case, the HIs. But instead of sending them all for a commitment, then he sends only a hash of them. He takes everything together and the hashes, and then just sends the hash. Okay, and this is a smaller digest. Now, what will the verifier do? Again, he chooses a challenge, and that's going to be that's going to work in as much of the same way. The prover sends all of the shares except for the one of the challenge, and then the verifier here it's a little bit different. How do you check with the hashes? Okay, first, now that the okay, they didn't appear in the correct way. Okay. Yes, sorry, I have to put everything. Okay, so first the verifier computes this HI for everything that he can, right? And he can do this for all except for one, right? Because he doesn't have the last share. And then once he has all but one HI, then he can compute the last one because he knows H, same as we did before. And again, this is with the discrete log example. So he can compute the HC, the H corresponding to the challenge, by taking big H and dividing with the product of all of the rest, right? So now he has all of the H's, 1, 2, n, and then he can compute the hash again, right? And then he can check whether this is indeed the hash that we got in the first, when we did the commitment, okay? So this is an optimization because when you're sending the commitments, you don't have to send all of them separately, you're just sending a hash. And there is some more work done on the verifier side, but I think, I don't know what the trade-off is there. So that is one optimization that we can do. Another thing that we can do, so these challenges, as I said, this protocol so that we amplify the soundness, right? Because the soundness was 1 over n. And then I said you need to repeat it a lot of times, okay? So there will be a lot of challenges that are sent. One thing you can do is you can, over here I'm talking about the different parties, yeah. So you can compute them from a seed instead of just, sending all of them. So for instance here, what do I mean you can compute them from a seed? Well, you can build this binary tree by starting from a root seed, and then from that you expand 2 values, right? You know what I mean by a seed? It's a pseudo-random generating function, right? It gets some input and then it expands it into a bigger output in a pseudo-random way. Okay, so you start with from the root seed, you build these other 2 seeds, and then yeah, each of them produce 2 children and so on. And then on the bottom you have, let's say, 16 values that corresponds to the 16 challenges. And then if I want to ask what does it change if I build the seeds this way? So if I want to ask no, these are the shares actually, yeah. These are the shares that we wanted to build in the MPC protocol, yeah. So if I want to ask the prover to send everything except for 1 challenge, and let's say that challenge is 5, then the prover needs to send me, instead of sending me everything, because now they are ordered, they are generated with a tree. Let's say here I asked for, the challenge was 5, so I want to have all of them except for the 5th one, okay? So that means the prover can send me S6, right? Because this he cannot send, because if he sends this, I can compute S5. Okay, so he can send S6. But then to send me S7 and S8, he can just send this one. To send me this 4 here, he can just send this one. And to send all of these branches, all of these leaves here, he can send this one. Okay, so then you are sending, instead of sending all of the shares except for 1, you are sending only a logarithmic number of shares, right? Because this is log 2. Okay, so that is one optimization that you can do. And then even better now, okay, so we said that, yeah, we can expand all of these shares from a seed. And I forgot to tell you how you make this work for the secret, actually. Okay, so you expand all of them from a seed, but then the last one, you have to adjust it with an auxiliary value, right? Because it has to sum up to the secret. Okay, so there are some workarounds for that. Okay, but then you can do this even better now with new improvements. You can use what we call the hypercube technique. And that one, I will go at a very high level on it, but you get the main ideas, and then when you read it, it's gonna make a lot more sense. So this the optimization technique is used to turn one MPC instance. Let's say you have an MPC instance with a number of parties that is equal to n to some d. Okay, so that was previously it was n. Now it's going to be it's going to be expressed as a power of some number. So starting from an MPC instance that you need to simulate for this protocol, you can instead simulate d NPC instances of n parties with this hypercube technique, and that is of course more convenient. So what is the main idea? Let's say here if you have if all of these squares here are your shares. Let's say you have, how many do I have here? 6 by 6. I have 36 shares, right? So I can rearrange them in well, now it's not a cube yet, it is a square, okay? I can rearrange them in a matrix like this, where each side is a square of this big number here, right? So instead of, let's say I have n shares, then this is a square root of n this side, and this is a square root of n this side. And then what I will do is that I will take per row, I will just sum up the first row and get something. I will sum up the second row and get something. I will sum up the third and so on. And then you do this on the other side as well. You sum up the columns. And you see now that I have also some values here. These values here, if you sum them up, they correspond to x, right? Because addition is commutative. So, because this was the sum of the first column, the sum of the second column. So if you sum all sums of columns, then you get your secret x, okay? So instead of just doing any shares, you rearrange them like this. And instead of keeping track of all of this, well, let's say one MPC protocol is not gonna have all this info in the squares, but it's gonna have only this info here. What happens here in terms of efficiency? Well, and what do I mean by this thing here? A technique to turn one MPC instance of n to the d into, or let's say square here, of n square parties into D instances, so 2 instances here of N parties. The first MPC protocol is going to be a square root of N party protocol, as I said, and this corresponds to the sum of the column entries. Okay? And the second one will correspond to here the sum of the row entries. And so if you do these 2 protocols instead of the huge one MPC protocol, what is happening? So how can you, the probability of cheating in both protocols, like imagine this is one, these are your shares of one MPC protocol. The probability of cheating on this one is 1 over square root of N. But then if you do both protocols, the probability of cheating in both multiplies again, right? So you get 1 over square root of N to the square, so then you get, and this should be only N, it's not a square root of N, you get exactly 1 over N, which is same as before, okay? So you get the same soundness, but you did fewer computations, you did only 2 protocols with, and this generalizes then. I will show you how it generalizes, and actually they found that the best trade-off is to take N equals 2. We will go into higher dimensions, but you always take 2 parties. Here I had N, some bigger N, right? It turns out that the best trade-off, if you calculate things, is exactly to take N equals 2, but to take higher dimensions. So for instance, if you take the dimension 2 only, this is what the protocol looks like, right? Instead of these 4 shares here, you have these other 4 shares here, like what I had before. And here it looks like I'm not saving anything, right? Compared to what I showed you before, where N was bigger and I was saving a square root of that. Here I'm not saving anything because here I have 4 values and here I have also 4 values. So for D in 2 dimensions, it's still not worth it. But if you go higher, so I'm going to show you cubes now in dimension 3. And the way that you infer which shares, which mini shares go into which MPC protocol is with this algorithm here. So yeah, like here it was easy because I'm looking at it 2D, and so yeah, this corresponds to the sum of these 2, this corresponds to the sum of these 2, and so on and so on. But if you want to look at it in higher dimensions, yeah, this is how you find which shares contribute. So for K, let's say K is your dimension. So first we're going to go, now we're going to look at 3-dimensional. So D is going to be 3 here. So for K in 1 to 3. And then you build the MPC protocol number K. And this is the shares that correspond, that are included in that protocol, that are included in the sum. So everywhere where every share whose kth coordinate is this J here is going to be one party. Keep this algorithm in mind. I'm gonna put it here so that we see what is what. So for instance, what does this look like in dimension 3? The first MPC protocol, so in dimension 3, remember you are supposed to get, because we are working with 2 to the 3 shares in the beginning, right? It is a cube, it has 8 values, that is 2 to the 3. Then you're supposed to get 3 MPC protocols with 2 main parties, okay? So this is the first protocol that you have, and these are the indices, how we denote them, 1, 1, and 1, 2. So the first MPC protocol cuts in the first dimension, that is the X here in the cube, right? X, let's say X is the first dimension, Y here, the vertical is the second one, and the third dimension is this one here, the Z. I'm going in depth. Okay, so MPC1, it splits in 2 parties. First, here you have this side that is highlighted, and here you have this side. And it corresponds exactly to when I say the kth coordinate has to be J for the jth party. So here the first coordinate is 1. And here, everything where the first coordinate is 1, I sum it up, right? So this corresponds to this side of the cube. And here I sum up everything where the first coordinate is 2, so it corresponds to this side of the cube, okay? So now I'm going to go at the other dimension, Y, for the next protocol, right? The next MPC protocol is going to be, MPC2, is going to be the Y dimension. So here it's going to be the sum of all of the shares where it was, the second dimension was equal to 1. So here, the first, let's say, the bottom row, and here you have the top row, right, for the other one. And then, yeah, the MPC3 is going to be divided on the third dimension. So first you take the front of this cube, and then you take the back of the cube, okay? So always the J coordinate. Now and this gives us, as I said, 3 MPC instances of 2 main parties. Now in dimension 3, we will have to look at it in a different way, right? No, I'm joking. We're going to look at both at the same time. Okay, so both cubes in dimension 4. So this is dimension 4, and this is the MPC protocol 1. So the party, remember, this is the sum of one main party, 1, 1. So you take the sum of everything on the left from the first cube and also everything on the second cube. And then the other party in the first MPC protocol will be these sides here. Okay, the second MPC protocol, again, so you're taking, on the one side, you're taking, in both cubes, you're taking the bottoms, right? And here you're taking the top. Again, it corresponds at the case coordinate, so the second coordinate, that is the y, should be j, so here it's a 1 and here it's a 2. Okay, and then when the third coordinate is equal to j, it's this division here, you sum all of these up, and for the other party, you sum all of these up. And then for the last one, it's going to be, again, the fourth dimension is equal to 1, so that means you sum up all of this and none of this, right? And conversely, yeah, this is what you sum up for the second party. Okay. So then you obtain 4 MPC instances of 2 main parties, and then this generalizes, of course. You can go higher and higher to see what the best trade-off is. And yeah, so if you go to dimension D, you will get D MPC instances of the 2 main parties, and this is a lot more computationally convenient for the verifier to check. And you remember, you're still checking everything when you're checking. If you're doing all protocols, you have covered all of the shares. They were involved in an aggregation of some of the MPCs. So you are checking all of the initial shares, but in a more efficient way. Okay, so that was briefly about optimizations. The main ideas, if you go read them now and see the protocols, it's going to be better. So in the NIST competition, we had a lot of these schemes. Yeah, if you look at the website, it's only these 3, 4, 7 that were categorized as MPC in the head. But then you have AIMER, which is also which was categorized as symmetric, but is also MPC in the head. And they are based on the different problems. The one that I told you about today was this first one, is the in the head. That is based on the syndrome decoding problem in the Hamming metric. So what we saw as an example. Then you have also syndrome decoding problem in the rank metric. You have one based on the permuted kernel problem, the MQ problem, as I said. I showed you what is MQ. I didn't show you what perk is. I didn't show you what min rank is also as a problem. But yeah, you can also do this with min rank, and 2 different teams have done it actually. Another one with MQ, but also with some additional structure, that was Biscuit. And then AIMER, as I said, is an MPC-friendly symmetric primitive. And out of all of those, now a lot of them stayed in the second round actually, because I think, yeah, let's say this is just my view, but it is, since you have this provable security property, and you found, you find hard problems that have been hard for a long time for many people, then there wasn't a lot of, things happening in terms of cryptanalysis for these schemes, right? Because they are, how can you attack this if other than attacking the underlying problem? And the underlying problem is something that we have been trying to attack for a very long time. So security is very much on the side of these schemes. Yes, and you see those that didn't make it are those that I said have more structure. I don't know if this, it might be an explanation. So everything else rested in the second round, and you have Mirit and Mira that did a merger because they were both based on the min rank problem, and so they needed to merge the 2 schemes so that we look at, don't look all of them. Okay, and I think that was everything that I had to say. So now I can take your questions. I have 2 minutes, and also on the break as well. Thank you.